Welcome back. Let's talk about buffers. A buffer is a solution whose pH changes very little when a small amount of acid or base is added. Most buffer solutions are made up of equal amounts. I mean, it doesn't have to be perfectly equal, but about equal amounts of a weak acid and a salt with the same anion. As a reminder, the salts are ionic compounds. So whatever's left over from the acid after the hydrogen ion is removed, that ion that's left over is going to be part of some sort of ionic compound. Acetic acid and sodium acetate, so the CH3 C double bond O, OH, and then the CH3 C double bond O, O minus, those two guys are a commonly used buffer. Together, they can keep the pH of a solution close to 4.7, even when a small amount of a strong acid or strong base is added. The buffers resist change in pH because added base, that extra hydroxide, it's going to react with the weak acid that's in the buffer. And if we put an extra acid, it's going to react with the anion, and it's just going to make more weak acid. When a small amount of this strong acid or strong base is added to water, big changes are made. So if there's no buffer around, take a look. We've got some water. It's reading at pH 7. Then they've added, this mole thing is just saying the amount. So a small amount of hydrochloric acid, that's strong acid, and woof, 1.7 pH, very, very acidic. Or I can start with the same amount of water and add in a similar small amount of strong base, and boom, 12.3 for the pH. I mean, this can change by over 5 pH units when there's no buffer in it. Now watch what happens. We're going to use the same small amounts of our strong hydrochloric acid and our strong sodium hydroxide base, exact same amounts to the exact same amount of solution, but this time there's a buffer in it. And it's starting out at 4.74 for its pH. So this is the one that has acetic acid and acetate anion in it. Now look what happens. My pH, after putting in the strong acid, it only dropped by 0.04. So almost no change to the pH at all after adding strong acid. And if I start with the buffer and add strong base, look at that. It only went up by 0.03. That's a big difference than when it changed by 5 pH units. In fact, we haven't mentioned it yet, but 5 pH units, that's 5, each one's worth 10. So that's 50 times more basic or 50 times more acidic. This one's only like 3 times more acidic or basic, much, much smaller amount. This is the acetic acid molecule, the weak acid. And if it loses its hydrogen ion, which can be written as H3O plus if it's in water, what's left over is the acetate anion, which is a weak base. Here I have, starting out with the original buffer solution, we've got equal amounts of the weak acid, the CH3COOH. Keep an eye on that H. That lets you know if you have an acid or a base. The basic anion is what's left over after H plus is gone. Let's take a look. Let's see, over here, they added in some acid, and they're representing that H plus as H3O plus. So they put in some extra acid. What happens? Well, the basic anion, he steps up and he's like, hey, I'm here to react and do an acid-base reaction. So he gets used up a little bit. His amount goes down. And in the process, look what happens. It just makes more acetic acid. Well, that's already in there anyway. And it makes more water, but that's neutral. That's not going to change the pH one way or another. So no big change in our pH. We're just making more of what's already there. On this side, they're adding some strong base. Well, at this point, my weak acid steps up and says, reporting to duty, I have an extra H plus here. I'm willing to give it to that hydroxide. We'll make water, again, neutral. And what's left over? Well, the weak acid lost his H plus to give it to hydroxide, and we're left with that same basic anion, the acetate anion. So all we've done is used up a little bit of our acetic acid and made a little bit more of something that was already there. This is how buffers work. They can react with small amounts of the acid or base that gets added for whatever reason, either in a lab or maybe in your body. Let's say, oh, God forbid, there's sepsis involved or something like that. It's going to change the pH levels in your blood. And your body has a buffer in it to try to counteract that change in the amount of acid in your blood. And they do that by just making a little bit more of something that's already in there. So let's focus on this human body thing for a little while. Our normal blood pH, I can move this box again, is between 7.35 and 7.45. So that's why I say 7.4. The body is able to maintain a very stable pH because the blood and other tissues in the body are buffered. The main buffer in the blood, and there's some other ones, there's a phosphoric buffer and stuff like that. The main buffer in the blood is the weak acid carbonic acid, H2CO3, the guy that's in soda, and its corresponding anion, bicarbonate, HCO3 minus. Do you see that difference? Take a look, make sure you can follow the hydrogen. Here the molecule's neutral and it has 2 hydrogens. Over here, it's down to 1 hydrogen and now it's got a negative charge. Somewhere nearby, there's a hydrogen with a +1 charge that fell off the acid. What happens? Well, the carbon dioxide that we breathe out, it's a waste product. And it has to get from our cells that produce the carbon dioxide. It has to travel through our bloodstream, reach our lungs, and then get blown out. And while it's doing that, it's in our blood, which is mostly made of water. Okay, well, those guys react, and they make this weak carbonic acid. At this point, the carbonic acid can fall back and create this, or it can break up into ions, the hydrogen ion and the bicarbonate ion. All right, well, this part over here on the right-hand side, this is a buffer system. We have a weak acid on the left, and on the right, we have the bicarbonate, the basic anion that's left over. Okay, well, with the carbon dioxide constantly produced by the different chemical reactions, the metabolic processes in our bodies, it will be transported by the blood to the lungs. The amount of carbon dioxide that's in our blood, that's what determines the pH of our blood. If you have more carbon dioxide, well, that reacts with the water and makes more carbonic acid. More carbonic acid can break apart into more hydrogen ions. More hydrogen ions, well, we saw on that pH scale, more hydrogen ions equals a lower pH. It's more acidic. I need to make sure that I keep the right amount of carbon dioxide levels in my blood. If a small amount of acid is added to our blood, to this carbonic acid bicarbonate buffer, let's say, what can add some more to it? Lactic acid. So this isn't a page in your textbook. One second. I wanted to show you on page 348 in your textbook. It gives you a few reasons if you're curious about what could change the amount of carbon dioxide levels in your blood, what could change the pH levels. or just sources of additional acids and bases. For the acids, you might get it when if someone's having a severe infection, sepsis, then that can accumulate lactic acid. That lactic acid will need to be neutralized, otherwise the blood pH will get too low. It'll become too acidic. Also, poorly controlled diabetes can lead to a buildup of keto acids, and that in turn can lower the pH of the blood. Meanwhile, if there's hyperventilation, so you're expelling too much carbon dioxide, that can raise the pH of the blood, make it more basic. If you've heard of people putting the paper bags over their faces when they're hyperventilating, the point of the paper bag is to capture carbon dioxide to try to keep that level a little bit higher in your system to try to prevent your blood from becoming too basic. So let's hold some of that carbon dioxide in solution there by rebreathing some of it in. They also say if there's too much vomiting, that can decrease the amount of acid in the stomach, which can then also lead to a rise in the pH levels. So let's say we're adding a little bit more lactic acid or keto acids to the carbonic acid buffer in the blood. Well, that small additional amount of acid will produce more hydrogen ions. The hydrogen ions can then react with the bicarbonate anion, and all it makes is some more carbonic acid, which is already there in the solution. If we do the opposite, if we lose some of the hydrogen ions from vomiting, let's say, or hyperventilating, well, our reaction's going to try to compensate for that. We'll end up creating perhaps more of the hydrogen bicarbonate ion and trying to replace some of the H+. So these are trying to compensate for any changes in the normal amount of carbon dioxide or acid and base levels in the blood. We're going to watch a video that briefly describes this bicarbonate buffer system in the blood. And when we talk about this buffer system, this is going to work for all types of buffer systems that may come up in both the body or in food preparation, things like that. Acids and bases and buffers are in all of those different fields. The code for chapter 9 is this one, that the term alkaline means basic. So I'll probably do the same thing where I'll give you a bunch of true statements and ask you which one of those is the code for chapter 9. And this is it, the fact that the term alkaline means basic. And we probably talked about that. Alkali, we've also mentioned way back in chapter 2 that alkali and alkaline mean basic. But keep that in mind while you're watching this video.
Let's learn about the bicarbonate buffer system. Blood is maintained at a narrow range of pH, which is between 7.35 and 7.45. Serious problems result from blood that is too acidic or alkaline. Abnormal pH can lead to coma and death. One of the ways by which the body maintains the blood pH is through buffers. The most important buffer in the blood is the bicarbonate ion buffer. Before we see how it works, let's review a little bit about acids and bases. Acids are molecules that tend to give up hydrogen ions. For example, hydrochloric acid dissociates into hydrogen ions and chloride ions. As a solution's hydrogen ion concentration increases, its pH goes down, making the solution more acidic. Bases tend to combine with hydrogen ions, neutralizing them to form water. For example, sodium hydroxide dissociates into sodium and hydroxyl groups. The hydroxyl ion combines with the hydrogen ion, neutralizing it. As a solution's hydrogen ion concentration decreases, its pH goes up, making the solution more alkaline. If there are too many hydrogen ions, or an increase in hydrogen ion concentration in the blood, the bicarbonate ion combines with the hydrogen ion to form carbonic acid. If there are too few hydrogen ions or a decrease in hydrogen ion concentration, carbonic acid dissociates into hydrogen ions and bicarbonate ions, thereby increasing the hydrogen ion concentration. We can use this equation to illustrate how an increase in hydrogen ion concentration, or acidosis, causes the reaction to move toward the left, which promotes the formation of carbonic acid. Likewise, a decrease in hydrogen ion concentration, or alkalosis, causes the reaction to move to the right, promoting the dissociation of carbonic acid into hydrogen and bicarbonate ions. In addition to buffer systems, the respiratory system also works to maintain pH. For example, if blood becomes too acidic, respiration rate increases in order to rid the body of carbon dioxide. A subsequent decrease in hydrogen ions occurs. Likewise, if blood becomes too alkaline, respiration rate decreases in order to increase the hydrogen ion concentration. You could say that hydrogen ion concentration follows carbon dioxide concentration.
Yes, you could. So that idea that, go back just one slide, what it's showing is, this is a really neat thing about chemical reactions. The idea that if I take away something, the reaction is going to shift to try to make more of it. So if the blood becomes too basic, so if we run low on H+ ions, the neat thing is that this hydrogen, carbonic acid is going to break apart to make more hydrogen ions. And of course, there could be more of this stuff around to break down or dissociate into H+ ions if we have more carbon dioxide. So I think it's kind of neat. It's like an alarm goes off and says, hey buddy, our pH is dropping. We need more carbonic acid so that it can make more hydrogen ions. And then if it goes in the reverse way, it's like, okay, we need the carbonic acid to form so that it can store hydrogen ions. And so that was the one here where if it's too acidic, we need to have it go the other way. We need these guys to react and form more of the hydrogen carbonate, carbonic acid, so that we have fewer H+ around. And that might be a good time to breathe out some carbon dioxide, get rid of it. Okay, I think that is about it. 1 second, I'll be right back. Last bit I wanted to go over was the lab assignment. There's 2 parts to it because we need you to first be able just to get comfortable with things that are more acidic and more basic. And I have a simulator online that will allow you to test the pH of some of the products. You're going to want to watch these 2 videos that I made with the instructions, and it tells you what the assignment is, what you have to do for the assignment. So you have to watch these. I think it's going to take you, including watching these, probably less than 30 minutes to finish, to take the pictures you need to take and submit them. So you're going to watch those 2. I'll have them also posted on the CHM130A Moodle site for the lab. The virtual lab simulation, I'll have the link there as well, but it's going to take you to this Amrita Labs to help you with the simulator. And then the second part that's not in this one, there's going to be some more videos on the CHM130A website that have to do with doing the pH calculations. Turns out you're supposed to be able to do those. So I made a video showing you how you can use your phones, or I found a video that shows you how to use your phone to calculate the pH if you're given the hydrogen ion concentration of a solution. So that should only take a few minutes as well to do. And since you watched this video, you know what the code is, so you can go ahead and take care of the participation quiz while you're at it. Thank you for watching. Let me know if you have any questions. You can always email me with those.